Good evening, welcome back. Before I forget, next week, for some of you, next Wednesday is a Friday because they use a period of Wednesday for some courses of Friday. However, I guess I will do it as usual here. So next week we have the lecture at 6:30 in this room, except if there is really, if it is really a big problem for too many students. So please, if it is a problem for you, let me know and we will see what we do. But I don't want to pass next week because otherwise we are going to miss one class. All right, let me remind you what we have done last week very quickly, and then today it's more algorithmic, and I think it's quite nice. Last week was a little bit boring. Last week, we introduced this notion of vertex connectivity and edge connectivity. It is when you have a graph, it's a number of either edge or vertices that you have to remove in order to disconnect your graph. And we say that G is k-connected if k, an integer, is smaller than this vertex connectivity. And we want to understand a little bit more this notion. We also introduced the notion of internally disjoint paths. So when you have two paths which have no common vertices except the two endpoints. And with these two definitions, we gave several characterizations of two connected unoriented graphs. So there were a list of several equivalent definitions for two connected graphs. Then we generalized these notions for two subsets. So we spoke about an AB path, so a path between any point in A to any point in B, and the notion of internally disjoint AB paths, which mean they do not intersect or they do not have any joint vertex except on AB. Be careful, this notion of AB separator I just mentioned last week, I gave a precise definition. If you slightly change the definition, you are going to get some contradiction. And this is an important point in mathematics. Be always very precise with definitions, otherwise you are going to face troubles. Okay, once you have this notion of separator, you can define the minimal number of vertices in an AB separator, or you can also look at the maximal number of internally disjoint AB paths. And quite intuitively, you will find out that these two notions are equal. These two numbers are equal. And this is indeed what is called Menger's theorem for a connected graph. If you have AB not adjacent, which means there is no direct edge from one set to the other one. So if they are not adjacent, you have this equality. If they are adjacent, you have to be more careful. And as a consequence, we get that G is k-connected. I gave the definition of k-connected here. If and only if, whenever you take two vertices, there exists at least k internally disjoint paths between these two vertices. So it's a characterization of what means, it's an equivalent characterization of k-connected and the number of paths between any two vertices. And in the last part, I will not say so much again about this. We had a construction which was called block cut point graph, how from a graph you extract the main information and you end up with a bipartite tree. So it's one way to remove the details and look just at the main connections in your graph. Okay, so this is what we have done last week. Always, if you have any question or remark, you can interrupt me or ask me by email. So today we look at chapter 6, which is called optimal traversal. Remember, traversal is a way to go inside a graph and to do something systematically. The first sections are quite simple. The last one is more substantial. About Eulerian trades, we already mentioned this. We already mentioned this probably at the second lecture. So let me come back just to this notion. this is just a reminder about Eulerian trade. So what it is, this, first it's a walk. A walk, you don't have any constraint. You can go back, you can visit one edge or one vertex many times. So it's a walk through. No. Yes, but I just recall what is a walk. It's a walk through all edges. Finally, only once. That's it. So a walk is without any constraint. If you add only once, it becomes a trail. Okay, and what? Yes, because this is a Eulerian trail. You go through all edges, but you visit them only once. On the other hand, you can visit vertices many times, and if closed, so it means if you start and end up at the same point, it's called a Eulerian tour. And if you have a graph with a Eulerian tour, you call it a Eulerian graph. So whenever you have a Eulerian tour in a graph, you call it a Eulerian graph. And you should have in mind one picture, because it's a famous picture, and you find it everywhere on internet. There is these 7 bridges of Königsberg. It is a first problem in graph theory, which is related to this Eulerian trail. So if you want to keep one image to keep in mind one image for Eulerian trail, look at what is Königsberg bridges, 7 bridges of Königsberg. And let me remind you also one thing, is that there is a result which says G is Eulerian graph, so it admits an Eulerian tour, if and only if, I just write IFF for if and only if the degree of x is even for any x. For any vertex. And this is quite easy. I mean, this is a simple statement, and the proof is also rather simple. And there is a proof of this as a report. So you can find this on the website. So it's an easy characterization of what is a Eulerian graph. G connected at the beginning. Yes, indeed. Thank you. And probably finite.
Yeah, it must.
If it is not finite, you have a problem.
It must be unconnected. Sorry, unoriented. If not, then we'll have to consider back in and back out.
Okay. If you have any question, just tell me. Okay, connected, unoriented, finite, and nice. Otherwise, the VIG will be unhappy. So this is an easy easy statement, easy proof, and also easy algorithm. If you have a graph with all degrees even, there is an easy way to construct this Eulerian tour. Now, what about extensions? I just want to mention this is rather easy. You can wonder, what about Eulerian trail? This is Eulerian tour, which means the starting point and the ending point are the same. If you assume that they can be different, how can you modify the assumptions? Because you impose less. If you accept that the initial point and final points are different, you impose less. Now, Say it again.
Only 2 vertices are on.
Yes. G admits Eulerian trail if and only if first the degree of X is even for all X in V minus 2 points, 2 vertices, which I just call XD and XF for departure and final, which means these two can have odd degrees. And you choose one of them as a for the starting point and the other one for the ending point, and you can realize a trade. This is again not difficult. It's slightly more difficult than the other one. What about, you can also do it for directed graph. If you have a directed graph, you can wonder what is necessary to have either a Eulerian 2 or a Eulerian trail. And it turned out that for Eulerian so it has to be a condition similar to this one. But now with orientation, can you guess what it? So when we have an orientation, we have one more definition. We have the degree in and the degree out. So you have vertices arriving at one point and vertices leaving at this point. So the necessary and sufficient condition is that the deg in of X has to be equal to deg out of X for Nx. So it means you have the same number of edges going to a vertex than the one going away from this vertex. And then you can do one more generalization. What about Eulerian trail, and not only two? So you admit that the first point is different from the last one. And you can guess for Eulerian trail in the directed setting. This is true if and only if deg in of X is equal to deg out of X for all X except 2. X final. And what about the first one? So you have the deg out of the first one is the first one. It has to be the deg in plus 1. You have one more edge starting at this point and the deg out. The deg in of the X final has to be equal to deg out of X final plus 1. You can check this is quite natural. So we have natural extension of this notion of Eulerian to Eulerian trail. And yeah, this is rather easy. Any question or remark or correction? Okay, let's move to something slightly more complicated about Postman tour 6.2. Postman tour. So let me directly write G connected, unoriented and final. I don't need to say it again. But now, with deg of x arbitrary, I don't impose that it's even or with one of these two conditions. So as we know, then an Eulerian growth is not always possible, of course, is not always possible. Okay, so far, so good. But then what you do, you remove the assumption that you are not allowed to go 2 times to the same edge. You're allowed to come back for some reason. So it means Eulerian tour is not always possible, but a walk through all edges is possible if some can be visited more than once, if some can be visited more than once. I remove this constraint. This is quite clear. And it's called, this is called a Postman tour. And indeed, the postman sometimes have to go on the same path. All right, but still, now you would still look for something which has a minimal number of edges. If you want to go everywhere, you don't want to, you want to minimize still the length. So we are going to put a weight on each edge. The weight can be 1. If you do it with a weight 1 everywhere, that's fine. And look for the walk or the Postman tour with minimum weight. And as I said, if all weights are 1, minimal weight means shortest. Minimum is equal to shortest. And answering this question or this problem is a optimal Postman tour. Finding this tour is called the optimal Postman tour. Okay, I hope it's clear for everybody. We're allowed to come back or to visit one edge several times, but still we want to visit all of them, but with a minimum total weight or minimum total length. Okay. And it turns out that there is an algorithm for this. And I think some have written a report on this. A few remarks. Looking for this, it does not correspond to the minimum. You could think that it's related to the minimum spanning tree, because for spanning tree, we also look for minimum total weight, but it's not the same problem. Why? Because here you are looking for a tree, and we have seen the one solution. While here, you want to visit all edges. So it means in the tree, some edges are not represented. So this doesn't help you. This algorithm doesn't lead to any solution for this one. So this is the first remark. And the second one, if G is Eulerian, which means if there is a Eulerian tour, so if you don't have to come back on any edge, then the minimal weight, what is the minimal weight in this case? It's just the total weight, because you go once over each edge. So this is a total weight, and you don't have to go back and forth on any of them. So it's just once all these weights. So the minimal weight is equal to the total weight. But in a sense, this is a boring situation, because you know that there exists one path going everywhere, and you don't have to look for minimum because it is just one of these paths. So in a sense, we want to avoid this situation. You are not, for this problem, you are not interested in a Eulerian graph because it's just too simple. So we will look for, I will tell you the algorithm for this, but I need two additional definitions before. Again, if you have any question, let me know. So what is a matching? You can guess with the word. So given G okay. This is a graph. So given G, a matching is a subset F inside the set of vertices. No, sorry, the set of edges. The subset of edges such that their endpoint are not shared. So what does it mean? You look for a family of edges such that the endpoints are never the same. So for example, here we have a matching. So I use the edges of the graph, and I take a family of edges such that there is never one endpoint for two of this family. Okay. What is a perfect matching? This is a perfect one. A perfect matching is when all vertices of D are endpoints of elements F. So in this case, you can see I touch all vertices. If I had done a slightly more complicated graph, then I couldn't find a perfect matching for this one. But this one has no, I mean, this is not a perfect matching. I don't know if there is a perfect matching in this one. At least there is no, I cannot just continue this picture and find a perfect matching. Maybe there is one, but this is not a perfect matching. Okay, maybe you can find a solution. Thank you. Do it. I'm not claiming that either there is one or that there is no one. I'm just claiming this is not a perfect matching. On the other hand, if we don't have this part, this is a perfect matching. Okay? Thank you. Okay, we need this definition. And yeah, the word matching is quite easy to understand. And perfect matching, it's perfect situation. Okay, we need this ingredient and we need one more ingredient. What is a complete graph? A complete graph of n vertices, and it's denoted Kn. Kn is a graph, there is only one, is the graph of n vertices with edges between all of them, between all vertices. So if you do it with 2, this is K2, quite simple. K3 is also quite simple. K4 and so on. So you have vertices and n vertices on edges going from any vertex to any other one. It's a simple graph. I don't want loops, additional loops, and I don't want multiple edges. Okay. How many, quick question, how many edges? If you are third or fourth year, you cannot answer. For first or second year, how many edges we have as a function of n? For complete graph. You are second year? Okay. What is your answer? Okay, I'll give you the answer. It's 1/2 n -1. N plus 1. Thank you. One. How many, this is slightly more, no, yeah. How many perfect matching? But I don't think this question is good. How many perfect matching? The answer is, I didn't check. This is what is called this double factorial. I gave the definition in the notes. And there is an example in the notes. This is called the double factorial, and there is a definition. But I don't think this is a good question, the perfect matching, because a more difficult question, and I don't know the answer, is how many non-isomorphic perfect matching. So first you observe that perfect matching are not possible for all n. If you have a odd number of vertices, you cannot have a perfect matching. On the other hand, if you have an even number, it is possible, but then you can wonder how many. And look at the picture in the notes. I don't remember if it is for K6, maybe. Yes, it's for K6. You can see many pictures are the same, or they look the same. It's just a rotation. So they're isomorphic. So question, how many non-isomorphic? But this is more difficult because the number of isomorphic one is depending on, or it depends on the matching you consider. Look at the notes and you will understand this question. I'm not sure it's an easy question. So if somebody wants to find, really to look for something more complicated, try to answer this question. I have written n plus 1. Here, n minus 1.
Just, yeah, that's what.
Yeah, but why I put n plus 1 in my notes?
I think because maybe you.
Okay, so please check. I will check if this is probably yes. I also prefer minus, but I'm not sure. Are you sure about minus?
Yeah, if it's not, then 2 versus 2.
Okay. So n,
Equivalent to N choose 2.
it's equivalent to?
Yeah.
Okay. But this was not the point. I define what is a complete graph. This was just additional questions. So now remember, my aim is to have an algorithm for the optimal Postman 2. So I have this graph with weights, and I want to find an optimal 2. So let me present this algorithm for optimal Postman 2. So what are the assumptions? G is connected, undirected. You can do the directed one, but it's more difficult. Undirected, finite, simple, so I don't want loops or multiple edges. And non-Eulerian, because if it is Eulerian, it's trivial. And that's all the assumptions. I consider the point xj. So the vertices are denoted by xj, and eij is the edge between xi and xj, if we have one, xi and xj. And since it is simple, if we have one, there exists only one. So it's simple. And I assume, or I denote by wij bigger or equal to 0, weight on eij. I assume it positive for simplicity. So this is a setting. And observe, I don't impose anything about the degree of each vertex. So what is the algorithm? One, I set x1, x2 to xn, the set of vertices, and I give the name S. Vertices of odd degree. You know, I'm here doing something which is quite natural. I decide that the first n vertices are the one with odd degree, and then I continue naming the other one when it's of even degree. So I just assume that the name for the first n corresponds to the one with odd degree. I just choose the name accordingly. Observe that n, is it arbitrary? Is it even, odd, or arbitrary? How many vertices with odd degree I can have? Yes, it is even. Otherwise, you would have a problem, one edge with only one endpoint, and is even. Okay. Now, a second point, construct n on S. What does it mean? You have, okay, let me do it only with 4. We have x1, x2, x3, x4. Then I artificially construct this graph. So it means here we have odd degree. So we had 1, 2, 3. Maybe, I can have observe that there is no contradiction here in having 2. Because we could have before one official edge here. So the white one are the one of G, then I construct the yellow one. So it's possible that we had already one edge, but I still construct a new one. Okay, so this one had odd degree, no problem, and I still construct the other one. And okay, no matter what happens there. So I construct Kn, or here K4. Now, I want to put a weight on K, on each edge of Kn. So I want to, so let's say this is a new, this is E12, but be careful, it's in yellow because it doesn't matter if I had already an edge here or not. It's a yellow one, it's a new one. I want to put a weight. Which one I'm going to choose? Not the one which could, or maybe not the one which existed before. I choose carefully the weight. So which we fix the weight on each edge of Kn by looking at the pass in G with between, okay, I need to give a name. We fix a weight yellow, I'm going to use yellow Wij for each edge of, by looking at the pass in G from xi to xj. And we have an algorithm for this. Remember, this is related to the Dijkstra algorithm. Find the path with minimum weight between two vertices. So even if we had a W12 in the oh no, this is 2, 3 here, 2, 3 in the initial graph, it doesn't mean that this is the best path between x2 and x3. Maybe there is a different path which give me a lower weight. So I fix a new weight on the yellow edge with the total weight of the path between x2 and x3 with a minimal weight. So fix a weight Wij for each edge of Kn by looking at between xi and xj. Okay, so now I have a new yellow weight everywhere. Do you have any question about this? Now I have this yellow part. I find a perfect matching in Kn, and I can't find it because n is even. Find a perfect matching in Kn with a minimum total weight. Look, I had weights, oh, here we are only looking for 2 edges. I had weights everywhere on all the yellow one. I look for the perfect matching. It's going to be complicated. Let's see. This one and this one, because the sum of the weight here and the weight here is the minimal one among all possible perfect matching. It's maybe not unique, but the minimal number is unique. So we have weights everywhere. I want to find a perfect matching. It's possible because n is even, and I just look for the solution with a minimal total weight. Okay. So far, we can understand. And now what are we going to do? It's rather clever. It's almost the end.
All this perfect match.
Okay, n is even. You can think about it. Yes, there is a perfect matching. If n is odd, there is no one. Is n is even. It's a complete graph, so you have all possible edges. So yes, it is possible. Then number 5. This is slightly, okay, we have to understand. Add weighted paths in G corresponding to this perfect matching. Okay. I don't think I can find a better sentence, but what it is. Look, we had chosen this perfect matching. We had a certain weight W omega or W23 and here omega 1,4. But these numbers were based on the real path in G. So I can just look at this path so that the total weight is this one and the path in G like this. It exists because I computed this number based on a path from this guy to this guy with a minimal weight and from this guy to this guy with a minimal weight. And what is the idea? I know I have to go back at some places because it's not an Eulerian graph, so I will have to go back. I'm going to go back on this very unheavy path. That's the point. I'm going to go back from x1 to x4, from x4 to x1, not on an arbitrary way, but by using this, which is one which costs less. So add weighted paths in G, but these edges already exist. Simply, I'm going to construct this path corresponding to this perfect matching. All right. And now this is what we have and what we observe. Then G plus these paths is a graph with even degree. So, yes. Look, this. So in a sense, I add this edge, but I add this path really because look, I had an odd degree here, and I add one more edge, and at this point, I add 2 edges, so the degree which was even is not changed. Here the degree is not. It's again even, and this one had an odd degree. Now if I add 1 edge, it's had this even degree. So I have changed the degrees at the odd vertices without changing the degree at the other one. Think about it. So G plus these new paths is a graph with even degree everywhere. And what can you do when you have an even degree everywhere? Yes, we have an Eulerian tour. So let me keep the picture. So we have even degree everywhere. Construct. So this is number 7. Construct an Eulerian tour. And the total weight is the minimal weight, or is a solution. Oh, the total is a minimal weight among all Postman tour. And this is clear. By this construction, you have constructed the best path where you have to come back with a minimal weight. So think about it, it's quite clever. You want to construct a Eulerian tour, and for this, you couldn't do it at the beginning because you had vertices with odd degrees, so you add paths, but you choose this path with a minimal total weight. And that's the solution. I'm not saying that it's unique. The minimal weight is unique. Probably the Eulerian tour is not. It's, yeah, you can start at any point. But even with a fixed starting point, I don't think it's unique. Yeah, you can. Okay. You can go backward also.
Sorry, like I'm like for this construction, n must be even, but is there a way to find such kind of optimal Postman tour if n is odd?
But it cannot be odd.
Yeah, I mean technically it cannot be odd.
It cannot be odd because if you had an odd number of vertices with odd degree, it means that there is one which has there is one edge with only one endpoint. So it's not possible.
Yes, I understand, but this like, is it not possible to like connect the graph with an odd number of points with odd vertices?
No, it's not. Because of you need a total even number. Yeah. So no, this n has to be even. It's not possible to have an odd n. If we had an odd n, then we would be in trouble because there would be no perfect matching. Okay, there are some extensions. Possible extension. This was the end of the algorithm. Possible extension, oriented graph. But then, you can do more complicated things. For example, you can have something like this with a different weight if you go in this direction or in this direction. And there are even additional complication, what is called the windy situation, which means that in some direction, it always costs you more than if you go in other directions. Okay, so you can make it more and more complicated. I'm sure you can find on internet plenty of extension about this. Yes?
Can you extend from here by deleting the new nodes we added and finding the Postman tour that is optimal without the additional edges?
No, because what means these edges? It means in order to, at the beginning, we know that it's not an Eulerian graph. So we know there is not one way to go everywhere without going back somewhere. Now we have added the place where we go back because these paths are the one which are the cheapest one. They have the weight which is a minimal one among all possibilities. So if now you are the postman and want to go everywhere, you will have to go through these two red paths at a certain point in your tour.
Let's get the Eulerian, right?
If you want to get everywhere, you will have to do it. That's the solution. So no, I gave you the final solution. I gave you not only the total minimal weight, but I also gave you, by choosing an Eulerian tour in this augmented graph, you have the solution. Okay, think about it. Next, except if you have any question. Next is about the Hamiltonian path. Things are not so easy with Hamiltonian path. You know, for the first two problems, we had a solution. The first problem was easy. The second one, I gave you the algorithm. Now, what about Hamiltonian path? Path on cycle and Hamiltonian cycles. I'm going to mention it. So what is a please. So just remind you what is a Hamiltonian path. It's a path through all vertices. But since it is a path, you are not allowed to go more than once, either on edges or on vertices. So it's a path through all vertices. If closed, it's a Hamiltonian tour or Hamiltonian cycle. We call it cycle. A Hamiltonian path or a Hamiltonian cycle. And let me emphasize in this section, no loop, they don't play any role. No loop or multiple edges. And it's quite natural. You can think the loop will not help you at all. It will not play any role. And multiple edges, if you have at the very beginning two multiple edges with two weights, and at a certain point we are going to look for a minimal solution, then you are just going to forget the one with a higher one. You are going to take the one with a lower one. So from the very beginning, I eliminate multiple edges. And there will be a part with orientation, part without any orientation. But as it was mentioned, there is no algorithm for checking if a graph has a Hamiltonian cycle. Oh, I should say no easy, because you can check all solutions and then you decide. But this is not really the best solution, because as soon as your graph is slightly big, it takes too long to check it. So no easy algorithm for checking if there exists a Hamiltonian cycle. And a graph with a Hamiltonian cycle is called a Hamiltonian graph. So if it has a Hamiltonian cycle, you call it a Hamiltonian graph. Okay, observations. For a Hamiltonian cycle, if it exists, only two edges at each vertex are used at each vertex. So it means if you have a complicated graph, and no matter what, you are able to do a Hamiltonian cycle, at this point in your cycle, you will use only two edges. Otherwise, it won't be a path. So at most, not at most. Exactly, you use 2 edges at every point if you have a cycle. That's quite clear. This is the first observation. And the second observation is when constructing such, when constructing a Hamiltonian path, it's not so precise, this sentence. No cycle should appear. So what do I mean by this? If you have a way to construct a Hamiltonian path, when during the construction you are not allowed to have a cycle, because it means that at one point you have a cycle, you won't be able to continue without visiting 2 times one vertex. So this is just an observation. If you do a construction for getting a Hamiltonian path, you cannot have a cycle at any point, because this would contradict. Yeah. And I gave in the notes, you can find a few examples, two or three examples of Hamiltonian path or Hamiltonian cycle. And in the notes, I just make a remark. I will not develop more here in the notes. I gave some sufficient condition on G to have a Hamiltonian cycle. But why these conditions are not very nice? Please look at these conditions. They are not very nice because they are sufficient, but if your graph is big, you need to have a very big degree everywhere. So the problem with this sufficient condition is the degrees are very big. And for many graphs, even big graphs, you don't have so many edges. So these sufficient conditions are usually not very pleasant. So it exists, but it's not very efficient. That the degrees are too large. Okay, so this was just a few things about Hamiltonian path. And now I even focus a little bit more. I focus on what is called the traveling salesman problem, which is related to this. 6.4. Traveling salesman. Being unconnected, weighted graph. Remember, we have different solutions for putting a weight. In this, we only put a weight on edges, not on vertices. You could also put weight on vertices, but what is considered here is the weight on edges. So we consider a connected, weighted, finite graph. And we look for a Hamiltonian cycle with minimum total weight. Now you should tell me, oh, but what you are saying something not correct, or your question is not correct. because what I said before, it does not always exist. I'm looking for a Hamiltonian cycle with minimal total weight, but you can easily construct graph for which it doesn't exist. So does it mean I ask a stupid question? No, it means when people, it's a hard problem. When people look for Hamiltonian cycle or with minimal total weight, they assume that there exists a solution. And how you assume it? You just construct enough edges. Because, suppose you have this with a weight W1, W2, and for some reason, you want to be sure that you can construct a Hamiltonian cycle, then you can always add artificially one edge and say the weight here is W1 plus W2. You're not really cheating, simply you fix your problem such that it has a solution. If it has no solution, why should you look for such problem? So you assume from the very beginning that there exist Hamiltonian cycles, and you are looking for the one with a minimal weight. So the question is well posed. You managed from the very beginning so that there exists solution. For example, by considering a complete graph. If you have a complete graph, you have a solution. So there are ways to get solutions by adding artificially some edges. So let me just mention, we assume, or we manage to have a solution. We assume that a solution exists. Now, there are two problems. If G is unoriented, we call this problem TSP for traveling Salesman problem, or small s TSP for symmetric. And if G is oriented, people call this ATSP for asymmetric. Asymmetric. And this one is symmetric. Is there one or two S asymmetric?
Asymmetric one.
Okay, so these, and as I mentioned, these are hard problems, and I will say more. Again, no loop, no multiple edges, because they don't play any role. It simplify our life. No, be careful, no multiple edges. In the case of oriented graphs, this is not a multiple edge, because the two directions are different. And we will assume, again, the weights ij are bigger or equal to 0. If you put negative numbers, it's more complicated. And as I said, we assume that there is a solution. Okay. So this is the setting of the problem. And fortunately, there exists an algorithm. There exists an algorithm for finding a solution, or a solution, for finding a solution of this of this, let me say ATSP or STSP. And this is called the Bellman-Helped CARP algorithm. Exists a solution. By the way, if somebody wants to study this algorithm, it's a good exercise. You can find plenty of things about this in the literature. But what is the problem? But its complexity, I haven't defined, and I will not define it. Its complexity is of the order O of n squared times 2 power n. So either you know what, I don't know a precise definition, but what it is, it means if you look at the number of computations you have to do in order to solve this problem, and if n is the number of vertices, you have to do a number of computation of this order. So n is the number of vertices. I'm not saying that you have to do exactly this number, but there is a meaning for this capital O. It's about this number, and you can see it grows exponentially because 2 power n is like exponential ln2 times n. So n ln2. Okay, so it grows exponentially. Yes.
This question makes sense. Are these algorithms proved to be the most
No.
efficient?
No, the question is it? Certainly not. It's not the most efficient one, but it gives you a solution. You are sure if you apply this algorithm, you get a solution, but you wait for a long time. So people are interested indeed in finding a faster. So one which wouldn't take exponentially long time. So there exists a solution, but still we are not happy because it takes too long. But if somebody wants to describe this algorithm, it can be done. And yeah, it's an interesting problem to how it works. But still, we would like to get something better. But there is a price. So we would like to get a faster algorithm. Faster means it wouldn't grow, the number of computations wouldn't grow like this. But so if we find one, that's fine. You will get some money if you find it. But the problem is, it has probably been proved that you cannot find an exact solution with a much slower, much faster algorithm. So still, it's an interesting question. You look for a solution which goes much faster, but maybe not with the optimal weight. So there is a balance. So we look to get a faster algorithm, but leading to a minimal, to a weight, leaning to a weight which is maybe not the minimal one, but close to it. So that's the price. You are ready to look for an algorithm which goes faster, but maybe with a solution which is not the optimal one, but you lose something. And there is a notion of, well, this is a notion of heuristic notion. I wrote a few things about this heuristic. a heuristic algorithm, it means you don't look for the optimal solution, but you weight it with the speed or with the accuracy or with the use of resources. Because if you have to pay for each computation, you would like to minimize the price. So you look for balance, the balance between optimal result and fast result. And there are ways to compare either the speed or the optimality, how close you are to the optimal solution. So I will state a few results in this direction. Do you have any question what we are discussing? So we look for a solution of this problem. We know it exists, but it's very slow. We look for something faster, but maybe not with the optimal weight, but something which is not too far from the optimal value.
In our early algorithm, when we were looking at perfect matchings, there was a double factorial. Does that make the complexity very bad?
No, but I didn't use this double factorial. Okay. I just gave, when I introduced these complete graphs, I mentioned a few things, but I didn't use these few things in the algorithm. But you're right, there is one in the previous algorithm. I didn't tell you how to find this optimal perfect matching. And probably you have to, if still your Kn has a big N, you have quite many possible matching. So you have indeed to look for an algorithm for finding the perfect one with the lowest weight.
Problem altogether, that was the optimal Postman tour. This is the trouble.
Yeah, but he asked a question about in the previous algorithm. Yes, I gave you one solution, but now if you want to implement it, and if n, the previous n is big, it doesn't mean it fast. But I gave you a solution. Then it's your job to find the best way to implement it. But this is not related to, it's a different problem. Yeah. Okay, so I'm going to work in this direction, not look for the optimal solution because we know it costs a lot, but look for something which is approximate. So I give you one solution for an approximate algorithm. So different, or I give you two different solutions or approximate solution or two different algorithms. For the symmetric Travell-Selman problem. So if it is symmetric, it means no orientation. And of course, I assume that it's connected and that there is a solution. So the first one, which is the most stupid one, start at x. Start at any x, and always choose the next edge. With a minimal. Let me give you an example, and it's also in the notes. Suppose you have this graph. I take it complete simply because I want to have a solution. So if you apply this algorithm, you start at x, you take the one with the minimal weight. You go here, you go here, you go here. And then unfortunately, in order to get a cycle, you have to go through this one, which means the total weight is 103, which is probably not the best one. So total weight. While you have, of course, solutions with lower total weight, but this is the most simple one. You just look, you are at one vertex, you choose the one with minimal weight. So this is easy to implement. So this is the most stupid algorithm, and indeed it gives you a bad answer in many cases, because you only look locally at what happens. So you lack the global approach. Now I'm going to do something more clear. I mean, better, but we can still be improved. But still, it's not so bad. The second one starts like this. We use the minimal spanning tree. We're going to, and we have an algorithm for constructing this minimal spanning tree. Why it's a good starting point? Because as long as you are pass on this tree, you know that it's optimal. The thing is, with a tree, you don't visit all. Maybe I do just a picture before. So if you have a tree, okay, suppose you have a tree like this, and you visit vertices along some path on this tree. As long as you are on this path, you know that because it's a minimal weight tree, you know that this is the optimal solution. The thing is, when you are here, you have to go somewhere else. So it means you suppose there exists an edge which goes here. But this is not optimal, of course. And then you continue on this tree. And again, when you are here, you have to do something. This is the idea of this algorithm. You use the information on the tree because it's a good one, but you have to jump sometimes to times, and you lose something when you jump. So we use a minimal spanning tree. So what we constructed in section 4.4 of section. So we first construct this tree. And we are going to duplicate it. I will make a picture. So let me do it in a better way. Okay, this is my tree. What I mean by duplicate, I construct something like this. Yes. I duplicate, so it means I consider one way to go down along one path and one way to go back along the other one. We duplicate it. Okay, and then we use shortcut whenever it is necessary. Of course, you have to be a little bit more precise, but what I did was correct. So you start here, you follow this path. When you are here, you don't want to go back to this vertex because you already visited it. So you jump from here to here. And you assume that there is a way to do it. I mean, if it is a complete graph, this edge exists, even if in reality it means you have to go back by a certain path you have already taken. Okay, when you are here, you jump again to either to the next point, which is the next one, which is not already used, is this one. Now you go down here, you jump again, you jump, and you go down. And, right, sorry, it's a little bit messy, but I think it's understandable. You use as much as possible paths in the tree, because these are good ones, but whenever you don't want to come back to the initial point, you jump. So it means I should have put some in different colors, the jumps. The jumps are here. This is also a jump. We have a jump here, and here, and this. Oh no, maybe not the last one. But of course, this is very rough in the sense that you have better jumps. This one has a certain weight. This one has a different weight. So it's not clear if it is better to jump from here to here or from here to another point. So you have to choose the most efficient jump like we did with this Kn. So you are looking, you look at all jumps you can do, but you are going to look for the minimal one. So let me be a little bit more precise. In the note, I have written a little bit more. So when we do this, we use part of the minimal spanning tree. And so this is optimal path, optimal, I would say local path, because they have the smallest weight, it's optimal local path, and get through some jumps. Which can be chosen carefully. And this is what we need to discuss. I know I need to do some parts which are not in the tree, but can I do it in a clever way? If you want to wait, you know, at the end of the day, I want two information. I need to know how fast is my algorithm, and I need to know how far I am from the optimal solution. Even though probably we don't know the optimal solution, but we still want to know how far we are from it. And there is an assumption which is usually taken, and it's a natural one. It is assumed that it's called the triangle inequality. The weight xz is smaller or equal to the weight xy plus the weight yz for any vertices x, y, z. And what does it mean? This is the weight, so we have x ratio, y, z the weight between X and Z is smaller than the weight between X and Y and the weight Y and Z. So this is called the triangle inequality. And if you think about real distance, of course, this is always true. But you need, why people impose this? It's in order to compare the different solutions. You have to have an inequality of this type. If you don't assume it, yeah, it's quite clear. If you don't assume it, if for a second this one is bigger, what are you going to do? You're simply never going to take this path. You will simply take the other one. So it's a natural assumption. Otherwise, you just forget this path. So lemma. Just to show you that people can say something. I'm not saying that it's easy. No, this one is easy to prove. And I think I gave the proof in the note. If G is undirected weighted, complete, and if this triangle inequality holds, then the solution given by 2, so this approach with the tree and this shortcut, so the solution given by 2 is never worse than 2 times the optimal value. Which is not so bad. So think about it. No, we don't have all information, but think about it. This algorithm was rather simple. Construct the minimal spanning tree, do these jumps whenever it's necessary. The path you get is at most 2 times longer. If you think about distance, it's at most 2 times longer than the optimal solution. Okay. But what is missing? What is the information missing in what I'm saying here? Sorry? I'm not saying how I do this comparison, and probably I don't know how to do it, but still there is something else missing. I'm not saying, and I don't know how fast is this, because you have to do a certain work for this number 2. You have first to compute the minimal spanning tree. And I don't know what is the complexity of finding this optimal spanning tree, or this minimal spanning tree. So if it goes also exponentially, this is not so interesting, because you wouldn't get so much in terms of time, and still you would have a solution which is at most 2 times bigger. So let's say 2 times bigger. On the other hand, if the complexity of spanning of this optimal or minimum spanning tree is, let's say, polynomially growing, not exponentially, but polynomially growing in n, then it starts to be interesting, because you know a polynomial grows much lower than the exponential. So in order to fully appreciate this result, you need to check exactly what is the complexity of the algorithm 2. And I don't know the answer, but this is what, if you want to get some money and find a balance between getting a cheap or a fast algorithm and an optimal solution, you should know the complexity of this algorithm. Now, okay, it's time. there is, it's written in the note, there, as I mentioned, when you have this tree, you have to do some jumps. You can find the best one with a construction similar to the KN I had introduced. If you look at the best jump, and it's called the Christofides algorithm. If you look at this improvement for the jumps, you can reduce this to 3/2. But you have to work a little bit more because you have to do the construction for finding the best jump. And again, this construction takes some time. So then you have again to compare the complexity of this new algorithm where you get a better approximation of the minimal weight, but you have one more step in your algorithm because you need to find the best jumps. So again, you need to compare these two things. I'm not saying that it's easy, but if n is very big, probably it's interesting to look for the best solution or optimal solution.
Is there a way if the graph conforms to certain properties to find algorithms that compute the optimal value more?
Yeah, so the question, I have to repeat the question because people cannot hear you. No. Of course, for specific graph, suppose you have the graph which is like this. If you have a very specific graph, of course, there are probably some better solutions and faster. I mean, in this case, you don't have so many solutions. But when we do these kind of things, we don't look for any specific graph. We look for the most general one. But then you are right. If you have additional properties, if you know that your graph has a symmetry or has some additional properties, how can you implement this in your algorithm and make it faster? Yes, this is certainly interesting. But yeah, these are the first step without any additional property. And then the next step is, you know something, you know additional things, how you can improve your algorithm. So it's a full subject. Optimization is a full subject. Okay. So I stop here. It means I covered essentially this section or this chapter 6. As I said, I've wrote a little bit more than what I presented today, but I will continue probably with next chapter next week. Thank you. And don't forget to prepare reports. It's important. You can see already many nice examples.